Alright guys, in this section we're going to look at reaction mechanisms. Usually when we think of a reaction we think of A plus B yields C, but that's not really what happens sometimes. Sometimes A plus B yields something else, and then that something else reacts with something else, and it keeps reacting with other things until finally, eventually, we get C. We don't usually look at each step individually. Usually we just look at the whole sum, the overall reaction, but in this section we're going to look at the steps. First off, we need to know that if we add the steps together, we're going to get the overall reaction. This is a lot like Hess's law from a couple of chapters ago. And that whatever mechanism it is that we choose, whatever the steps are that we choose, that they have to agree with the rate law that we determined experimentally. And we're going to see at the end of this section how to do this. The stepwise reactions, or the elementary reactions, can usually be described as unimolecular, with a single molecule being involved, bimolecular, with 2 molecules, or termolecular, with 3 molecules. Termolecular reactions don't happen very often because the reactions have to be simultaneous. That means that all 3 molecules have to interact with each other at the exact same time, which is not that common. Whenever you take elementary reactions and put them together, you're going to be getting a multi-step mechanism. In a multi-step mechanism, there will be intermediates. An intermediate is something that gets made during one reaction and then gets used up during a different reaction. So it's not really a reactant, it's not really a product, it's something that just shows up and then is gone. You can figure out the rate laws for the elementary reactions by looking at each elementary reaction individually. For example, if I take a look at this elementary reaction with just one reactant, I get a rate law that looks something like this. If I have an elementary reaction that looks like this, which is another way of writing this, then I get a rate law that looks like that. Okay, this type of reaction gives me this type of rate law, and so on and so on. Hopefully you see the little pattern here. So you can figure out what the rate law is by looking at the elementary steps. So let's take a look and see how to do that. Now, the important thing to know here is that how fast your overall reaction is going to go is going to depend on the steps, but it's not going to depend on all the steps. It's only going to depend on one step. The step it's going to depend on is the slow step. This is a lot like an assembly line where you have 3 guys working on something. One guy's screwing on a bolt, another guy's gluing something, another guy's putting it in a box. Alright, if the guy doing the bolt and the guy doing the box are fast, but the guy doing the gluing is really slow, then how much product you can make is going to depend on the slow guy. It's the same way with reactions. How much product you can make depends on the slow step. So it's the slowest step that determines the rate. So that's the one that you need to focus on. Don't worry about the other reactions. If your first step is the slow step, that's really easy. All you have to do is use it as the rate law using these little guidelines right here. But if the other steps are the slow steps, that gets a little complicated. So if any other step is your slow step, then you have to combine that step with other steps that came before it. So let's take a look at an example of this. First off, this right here is our overall reaction. And then over here are stepwise reactions, our elementary steps. Here's reaction number 1, here's reaction number 2. Now if you added these 2 reactions together, then you would get your overall reaction. Notice that we have an intermediate here, NO3. It gets made in the first reaction, but then it gets used up in the second, so it's not included in the overall reaction. Now if your first step was the slow step, then your overall reaction would just depend on the reactants in your first step. So it would just depend on these 2. So if I take these 2 and I add them together, I'm going to get a rate law that looks like this. Alright, this is just like what we saw right up here in this example right here. But if your second step is your slow step, Then it gets a little more complicated. If your second step is your slow step, then it's going to depend on the second step. And notice I'm just using the reactants. Products are never part of rate laws, it's always reactants. So I use my second step, and I have to use my first step. And so I get this rate law right here. Notice that my intermediate is not a part of the rate law. So let's take a look at one more example. In fact, why don't you go ahead and try this last example on your own. Pause this, see if you can go through and do it, and then we'll check it and see if you got it right. So to figure out your overall reaction, you're just going to add these two together. Notice NOBr2 is your intermediate, so it's not a part of your overall reaction. And so if we work this out, we get this reaction right here. And one way you can possibly check yourself is make sure that the reaction you come up with balances. If it does, then you might be right. If it doesn't, you're definitely not right. You need to go back and fix it. Now let's take a look at the second question. What would the experimental rate law be if the first reaction were the slow one? Let's try that one. So if your first reaction was a slow one, it's just going to depend on these two reactants here. And so we're going to get this rate law here with just these two reactants. And then for our last question, what if the second step was a slow one? If the second step is a slow one, it's going to depend on your second reactants without your intermediate plus your first reactants. So we get a rate law that looks something like this.